Hello, my name is Christopher Faudinelli. I'm a Senior Solutions Engineer here at Altair, and I'll be going over how to validate your suspension design and vehicle dynamics. So, are these questions keeping you up at night? How do I balance time spent in building the virtual model versus the race car? Is it feasible to test virtually in the absence of design data? Will everything fit into my wheel end package? How do I reduce the weight of my car by using dynamic road loads? How do I use FSAE tire consortium data to drive vehicle design? Can I predict the handling of a new car before it's built? Well, to answer all these questions, what you need to do is you need to build a MotionSolve model. So now you may be wondering, what can you even accomplish with MotionSolve? MotionSolve is a multi-body simulation software that helps you easily build and execute complex system models to evaluate the dynamic response of products and optimize the performance. Areas that we specialize in: kinematics, so studying the motion of an end effector; static and quasi-static simulation to study the compliance of a suspension system; dynamics, studying the load on an aircraft landing gear; frequency, we can extract loads for durability analysis or study low frequency for NVH. And then multiphysics, where we can perform multidisciplinary analysis, a couple of other products like controls, CFD, and bulk particle data material. MotionView offers a seamless end-to-end solution for multi-body simulation as part of the HyperMesh desktop environment. It provides a comprehensive pre- to post-processing development experience for complete simulation management. Because of how easy the interface and tools are to use, MotionSolve beginners without any domain knowledge can easily assemble full vehicle models. You can define and simulate a duty cycle events and automatically post-process relevant results. So, assemble. We can efficiently create complex multi-body models in MotionView thanks to its user-friendly interface, intuitive workflows, and numerous ease of use utilities. We can streamline the process of assembly-wide modifications using parametric expressions, internal or external scripting, and multi-system adaptation. Solve. Using Altair's multi-body solver, MotionSolve quickly and accurately simulates your assembly using either the online or offline method to view animations as the simulation solves. Evaluate. We can leverage essential post-processing tools like Hypergraph and Hyperview directly within the MotionView interface for seamless transition from modeling to plotting and viewing results. We can also select from pre-existing report templates, or you can design your own to automatically generate event-specific animations and standard event plots. Now prove. We can improve design with optimization tools like MotionSolve, Optimize, HyperStudy, all within your MotionView session. You can conduct not just CAD-based optimization, but also coupled structural, electrical magnetic, CFD, thermal, and multi-body dynamics optimization. To show you how seamless MotionView is to use, let's head into a demo where I generate a front suspension from our FSAE library and go through the setup and verification process. With MotionView loaded, we need to load the Vehicle Tools extension. So let's go to File, Extensions, and Enable Vehicle Tools. Once that is done, we're going to get a new ribbon called Vehicle Tools. And we can see that we have what's called a library. By default, it is set to the car and small truck library. I'm going to update it to a user custom library for the FSAE and Baja library. So I'm going to need to update the assembly wizard, task wizard, standard include model, as well as the wizard library directory. With that complete, I can now access the assembly wizard and load in the Formula SAE and Baja library. For this example, I'm just going to load in the front suspension. With the suspension loaded, we can see that it's organized within a few systems. The first one is the body fixed to ground system. This just contains the vehicle body joined to the ground by a fixed joint. We'll be updating the full vehicle body more in the full vehicle analysis. Now the main one, which is the front suspension system. It includes all the corresponding bodies, control arms, push rods, rockers, bushings, as well as a few other sub-assemblies for the shock absorber and the front coil spring. We also have a well-defined system for the rack and the steering column. Last, we have a system for tires. So these entities correspond to external tire files. If you have any files from suppliers, you can input those files here in .tir or .tpf format. So when you're constructing your model, you're going to have lots of data that you need to import. So we have a tool called Data Summary, where we can import points, vectors, curves, bodies, bushings, joints, and much more into the Motion View model. We can export these as a TXT or SLK format. Once we've done all our updates, we can import that SLK file back in, and it'll update all the corresponding entities that were in that file. Once we have all of our entities updated, we can now predict the performance of the suspension. One of the first ways to do this is through the kinematics and compliance test, where we validate the suspension in ride, roll, and steering events. So if we go to the vehicle tools, events, and general, let's select the KNC analysis. It's going to first load jacks in at each wheel end. In the entity editor, we can define which types of events in the KNC analysis to perform. I am only going to perform the ride, roll, and steering. Now for the vehicle parameters, I'm going to change the mass to a more reasonable value, like 220 kilograms, as well as change the steering wheel angle to 160 degrees. We can additionally alter the suspension travel, the static loader radius, and the vertical spring rate of the tire. Before doing anything else, I am going to quickly save the model. When running analysis, I do prefer running it in offline in XML format. I also like to change the output directory to a new folder where all the results will be stored. With the analysis complete, we can load a fully detailed report for each vehicle event. This report is added to our session, allowing us to navigate through each test, which is the ride, roll, and steering, as well as view an animation at the end. For each run, an SDF file is generated. This file contains various amounts of data for each time step, for example, ground reaction force, the toe angle, camber angle, Ackerman steering, and much more. To determine the max wheel cut angle at the full steer lock, as well as the turn radius of the vehicle, if we navigate to the full steer lock, which happens at 22.5 seconds, we can view the steer angle and the Ackerman curve to curve diameter. Now, I'm going to change the suspension design to see how it impacts the overall kinematics. Right now, I'm just going to update the outer tie rod ball joint. This should primarily affect the toe and Ackerman steering. I could update this through the data summary, but I want to show you how to update points manually. I'm also going to update the push rod outer point, and this should have an impact on the ground reaction force, camber, as well as the toe. Overlaying the reports, I can see changes in toe, as well as caster, a bit of camber, and some changes in the ground reaction force and the wheel rate. When the steering is fully locked, we can observe a significant impact on the wheel cut angle and the Ackerman results. Now I'm changing the upper and lower ball joint positions. This should have an impact on the caster and camber compliance. Overlaying the results again, we can see a significant impact on toe, caster, as well as the camber. Looking at the SDF report, we do not see any significant impact on the wheel cut angle or Ackerman results. To test the packaging of our system, we can add a collision detection in Hyperview. For example, I'm going to be using the tie rod and knuckle as my first group. And then I'm going to be using the lower control arm and the push rod for my second group. I'm going to change the proximity check to about 50 millimeters, and I'll show the results by elements. By reviewing the animation, I can determine if the parts will collide or interfere. Now, I like to determine the loads acting on the suspension. And one way to do this is through a static load analysis. But first, let me import a system with force outputs already defined. Looking into the system, I can see that there are only 7 outputs. They are all set with the type of force, and they are set to the left bodies in the front suspension. Returning to the entity browser, I'm going to load in the static load analysis. Whenever you load in a new analysis, it becomes the active one, while all the other analyses are deactivated. In the entity editor, I'm going to update the front and rear mass. For this example, I'm setting it both to 110 kilograms, and I'm going to leave the SLR as default. I can check the default load cases applied, and by default, there is only a self-vertical load that is being applied. When defining additional load cases, I tend to use the 1, 2, 3 scenario, where there's 1G lateral force as for left and right turns, a 2G longitudinal for braking, and then a 3G vertical for worst case loading. I'm going to now create a 1G lateral load to simulate a left turn. I need to ensure that the load case numbers correspond to the correct scenario and the titles make sense. For example, 1G left turn. I am going to be applying it to the tire contact patch. I also need to make it symmetrical on both sides. For this case, I'm changing the direction to Y, and since it's a left-hand turn, the forces act in the negative Y direction, so I need to include that in the multiplier. I'll reuse the same loading value at each wheel end and set the intervals for the result output. Now, I'll add additional rows for remaining load cases and activate them all. Alright, after some movie magic, my load cases are populated. Just to recap, I created a 1G right turn in the positive y direction, a 2G longitudinal braking in the x direction, and then a 3G vertical load for worst case scenarios. With everything set up, I can now run the analysis. Once the analysis is complete, I can view the results in Hyperview. I already have a vector plot loaded in to show the directional loads acting on the suspension. So, how do we export these loads to an ASCII or FEA format? Well, to answer that, we have a tool called the load export. It can be accessed through the Analyze ribbon. If we open it up and then navigate to the results location, there will be a .meta file that is created from the force outputs. We can select any or all the components that have a force output corresponding to it and retrieve forces at any or all of the connections. I'm just going to do the wheel hub for right now, and I can choose the time steps that I want to export the loads for. I can either do all the time steps, some peaks, a range, or bring in my own CSV file. Once I hit apply, I can start exporting the loads. I can either export it as a table summary or as a PDF file. I can select the node IDs that are going to correspond to my FEA model. If I hit apply, I can then export, define the location, as well as the file name. As you can see, DAT and subcase file were created. I can also export this as a tabular summary. I'll export to the same location. And now I have a txt file showing the loading at each time step at the wheel hub. Well, that is all for this demo. Now let's go back to the slides. Once you have verified each axle suspension, you'll be 90% complete. For the last finishing touches, you'll need to generate a full vehicle model. The workflow is simple. You'll need to export the suspension and steering systems from your half-car models, build a default full vehicle from the assembly wizard, delete the systems from that full vehicle that you're going to replace. Now import those half-car model systems. And once that's done, you're going to update your mass, inertia, and any damper properties. Then choose a dynamic test. This could be a straight line or cornering, and then run. You can view reports at the end. That concludes my presentation and how you can utilize MotionSolve to verify your suspension and vehicle dynamics. If you would like to explore our products even more, please check out our available online resources. Now we'll head to the Q&A period.